Okay, so today we're going to talk about Newton's third law of motion. And the third law, like the first and the second law, also has a common name, and the common name for the third law would be the action-reaction law. And the reason that it's referred to that way is because of the way Newton expressed the third law. He said that for every action there is an equal but opposite reaction, which is a completely accurate way of thinking about the third law, but it maybe hides what the third law is really about, because it may make it seem like it includes things like sociological or psychological things, where one person creates an action and then as a result of that people around them have a reaction. There is some truth to that, or some analogy to the way people act that is similar to the third law. The third law is talking about the physical reality, and so therefore it is not concerned about any sociological or psychological effects. It's specifically talking about the forces that are acting on objects. So maybe a little bit more articulate way of expressing the third law would be to say that for every force there is an equal but opposite force, and that we could actually write an equation. So if I find that there is some force F1 that is acting on some object, then whatever object it's acting on is going to create an equal but opposite. You really literally would read this equation like this. F1 is equal but opposite to F2, the return force or the reaction force. So that expresses the third law, and maybe a little bit more clear that it is only referring to the forces that act on objects, but still maybe is a little ambiguous as to where is the source of the two forces. So the last way I'm going to explain to you the nature of the third law is to give you the most articulate version. It's a little bit wordy, but it makes it a little bit more clear what we're talking about. So for every force that body A or object A exerts on object B or body B, there is an equal but opposite force exerted by body B onto body A. So body A pushes against B. B therefore is going to respond by pushing back with an equal force but in the opposite direction. So we could write that like this. The force of A acting on B is equal to but opposite to the force that B exerts on A. So that's probably the most articulate expression of the third law. And it's a very conceptual thing. That the third law is used for all kinds of aspects of thinking about why objects move the way that they do, or the fact that objects are able to move at all. In particular, the thrust force. The thrust force is really important to think about. When you think about objects that propel themselves forward, they don't do it by propelling them against themselves. What they do is they push against something. So for example, when you want to walk, you're going to push against the floor, and the floor is going to produce an equal but opposite force. So if you want to move in the forward direction, you do so by pushing backwards. If you just think about that, the next time you stand up to walk, just think about which way you're pushing on the floor. You push backwards in order to propel yourself forward. If you want to walk backwards, then you push forward on the floor, and as a result of pushing out forward on the floor, the frictional force between your foot and the floor will allow the floor to push back against you, and that produces the force that actually begins to propel you forward. So anything that is moved by the process of thrust, or is able to propel itself forward, it always does so by pushing against something. So when we walk, or we ride a bicycle, or we are in a car or a motorcycle, we push against the ground. When we're in a boat, we typically are pushing against the water. And then if we're in the air, if we're flying in an airplane or in a helicopter, then we're pushing against the air. We push against some object, and that object pushes back. And believe it or not, if you push hard against the air, you can push hard enough to propel aircraft up to 600 miles per hour, or even faster for military jets. They can get up to more than 1,000 miles per hour by only just pushing against the air. The air pushes back with enough force to propel those objects forward. So the third law is crucial to the idea of propulsion, how all forms of propulsion work. And I'm going to leave out rockets because we'll talk about that one in class. But the third law really helps to explain why any object is able to move at all. It does so by pushing against an object, and then that object pushing back is what propels it in the direction that it's moving. So let's take a look at another aspect that you're going to be asked to think about in terms of the third law, and that is identifying points of third law action. So that is to say, looking at places in an object's motion or in a description of an object and thinking about where would there be an example of this interaction pair, this action-reaction force. it's going to be super important to think about how the action-reaction force, the law, I should say, is different from the first law. So I'm going to look at this example of Brenda pushing a box across the floor at 0.5 meters per second. So this is an example of no acceleration in any direction. The box is not accelerating up or down, and the box is not moving left or right. So let's draw a picture of or a free body diagram of what the box looks like. So I'm going to draw the free body diagram over here to the left. So obviously there would be weight acting on the box. The floor is pushing up on the box from underneath. That's going to produce a normal force. And then we know that Brenda is pushing. I'm going to call that F of B for the force that Brenda is exerting on the box. And since I know that the box is not accelerating, that means there must be an equal but opposite force pointing backwards that is coming from the friction. Okay, and at this point it might be, it might feel right to say that, look, there's the weight and the normal force, and they are equal to each other and they are opposite to each other. That's an example of the third law. But that is not an example of the third law. That's an example of the first law. And one of the things that would tip you off that this is not a way you would describe the third law is that both these forces are acting on the same object. So the third law doesn't look at the forces acting on one object. It always, 100% of the time, is always looking at two objects. There has to be two objects where the forces are acting. So while this free body diagram shows lots of equal but opposite forces, it is only an example of the first law, not the third law. So then how would the third law look different? So let me draw a very large picture of the floor. We'll say, for example, maybe this is a refrigerator, and we are going to push against this box. Okay, so here we are, pushing against this enormous box. Very difficult to move, but it is, let's say that it is sliding, right? So it's sliding across the floor at 0.5 meters per second. Not a very fast speed, but very important to recognize it is moving at a constant speed. So it is true that the forces adding up on the box do add up to zero. But if the question is a third law, so these are called third law interaction pairs. Okay, so let's take a look at the things that are happening with the box. So first of all, we said that there was a normal force being exerted by the floor onto the bottom of the box. So that would be right here. There is the normal force from the first law description of this problem. Okay, but the box also has a solid surface. So it's not just that the floor pushes against the bottom of the box. The bottom of the box also pushes with an equal but opposite force with equal value. So the floor and the bottom of the box are both experiencing that normal force. It's not just one object. This one was just showing me the forces acting on that box, but not showing me the forces that were acting on the floor. But I know there would be an equal but opposite force according to the third law. Now, if the box is being pushed in this picture to the right by Brenda, then that means that there must be a frictional force acting on the box. Here's the frictional force we were just talking about. But where's the equal but opposite force? It's acting on the floor. So that frictional force is acting on the floor also. You might say, but I don't see the floor moving. So like, how would I know that that frictional force is there? But just imagine if we put this on some kind of trolley or on a cart with wheels. When you push on the box, for some reason the trolley moves, right? The cart moves. Why does the cart move? Because the frictional force has been reduced between the ground and the trolley, but between the surface of the bottom of the box and the cart, there's still frictional force. So what drives that forward is the frictional force between the surface of the box and the surface that it's sitting on. That frictional force is there. Now you don't see it in the floor because the floor is attached to so many other things. There's so many other forces acting on the floor. So you're not going to push hard enough on the floor to make the floor begin to accelerate, but the floor does experience that force. If you could look at the temperature of the floor, you would see the floor is warm where you pushed across it because of the force that you were exerting against the surface. We'll talk about that in later chapters, about that aspect of energy. But the floor definitely feels that force. And so when I draw these two, if you notice, I draw them on different objects. Here's the force acting on the box. Here's the force acting on the floor. Here's the force acting on the box. Here's the force acting on the floor. Now there's still one more force, because we said that Brenda is pushing forward on the box, so therefore the box is also pushing backwards with equal force. Whatever force Brenda pushes on the box is going to push back against her with that same force. Okay, so that takes care of almost all of the forces that are acting on the box, except for one. We did not look at the weight arrow. The problem with this one is to think about where is the other force, right? So for every force, there's an equal but opposite force. So the Earth exerts a force on you, okay? So then where is that equal but opposite force? Well, if the Earth exerts that force on you, then you must exert that force back on the Earth. So that's a little hard to draw in this diagram because I only see the floor, I don't see the entire object. But we can try to draw a little bit bigger version of this. So here is the Earth. Here's the box sitting on the Earth, and that weight arrow that we're talking about right there would be acting on the box, pulling the box towards the center of the Earth, but the Earth would also feel that force. Now, would we call it W? It's equal to the weight of the box, but I don't know if I would call that the weight of the Earth. It doesn't really make sense to think of that as the weight of the Earth, but it is a force that acts on the Earth. Instead of calling it W, we might instead call it F of G, for the force of gravity, right? So your weight is the force of gravity acting on you, but you also exert that force on the Earth. And the reason why you don't notice it on the Earth very much is because the Earth is so large. You don't notice the effects that you have, but you do exert a force equal to your weight on the Earth according to the third law. So each of the forces that we saw in the first law, there was an equal but opposite force, but we had to look at the things that it was interacting with. So we had to actually look at Brenda in this case. We had to look at the floor, and we had to look at the Earth to think about where are these other forces that are acting. So these are all conceptual ways of using the third law to talk about propulsion or to talk about these interaction pairs that are places where you can identify, here's the third law at work. These are all conceptual ways that you can demonstrate your understanding of the third law. In the next video, we'll look at some of the calculation problems that you can make with the third law.